So welcome everyone to today's webinar with Nick Kotov. He will talk about graph theoretical descriptors for biomimetic nanoparticles and fibrous nanocomposites. They're a very exciting topic as part of the HDR seminar series. And Nick is the Irving Langmuir Distinguished Professor of Chemical Sciences and Engineering at the University of Michigan. And he demonstrated the ability to self-organize into complex structures as a unifying property of all inorganic nanostructures. He developed a family of bio-inspired composite materials with a wide spectrum of properties. And so that includes nacre-like, ultra-strong, transparent composites, enamel-like, vibration-isolating composites, and a lot of other very, very unique materials. And so thank you very much for being here. And we look forward to your talk.
Thank you very much, Hendrik, and thank you all for being a part of this meeting. Let me start sharing the screen. I have to say that it's all work in progress, and I very much appreciate any kind of critical comments. You will not hurt my feelings by all means. I kind of used to all that from my childhood. Let me start by thanking many contributors to this work. So first of all, my good colleagues from University of Michigan, Scott Van Epps and Angela Violi, they have helped me with the part of the project which is related to the proteins. And Paul Bogdan was a part of it, but also he was a part of the project on composites, which was also involved 3D Nepal. And I need to thank also the funders, because this was a kind of a big jump for me. And I would like to express a lot of gratitude to the Department of Defense for the Vannevar Bush fellowship. It gives a lot of freedom, and I use this freedom for this work. And the Newton Award. It's these awards had funded these wonderful students. Minjong and Michelle and Sonera, they were involved in the proteins, and Drew had been involved in composites. So let me motivate the first project on the protein by this very recent paper. It's actually just a couple of weeks old, and it's related to the effect of nanoparticles on inhibition of SARS-CoV-2 virus. Unless you have been, interested in how the inhibitors work, I'll give you a brief explanation of that. So there are spike proteins, basically the sensor heads on the virus, and they are attached to the complementary protein on the cells called ACE2. And after that, they start invading. The formation of the protein-protein complex that you see here is the first important step. And in order to create a drug that prevents the penetration of the virus, one needs to block the spike protein. And there are actually many biological drugs which are being developed at. And that's how actually antibodies are operating too. So What this group in Turkey and Spain have found that the graphene oxide nanoparticles, they very efficiently block and form the complexes with the spike proteins, up to 100% inhibition of infectivity. The nanoparticles are very broadly sized, and it's not clear which part of them work, but considering that the inhibition is very strong, some part of it works very efficiently. And understanding and engineering these particles is the next step, is the direction. It is actually can be related to the number of studies which had been done at the interface of the nanoparticles and viruses. There were many papers that nanoparticles inhibit many of these viruses. Silver, gold, zinc oxide are the primary participants here. It's not very clear what is the mechanism of that. And as you can see, the variety of sizes, variety of chemistry, there are plenty of engineering parameters which are not controlled here. And it's efficient and essential to understand better. It works, but it's not very clear how. A few years ago, we actually looked, about 11 years ago, we looked into how the nanoparticles could interact with proteins on the basis of their structural analogy. And as you can see, there are many lines of comparison, for instance, size, charge, the surface chemistry, where the proteins and water-soluble particles are actually quite alike. If they're alike structurally, they can form the protein complexes. Of course, there are many differences between them, and how to reconcile these differences and the similarities is the main question. At that time, we started a number of projects which are kind of similar to the protein-protein complexes that you saw with viruses, but in this case, these were antibiotic-resistant bacteria, and found that depending on the size and shape, the nanoparticles of zinc oxide exhibit very different inhibition of essential enzyme. And again, it's not very clear how we can improve that unless we design a certain set of descriptors of the particles in order to account for the formation of the protein-protein complex. At that time, we postulated that the difference in shape is related to the difference of how the particles fit. Is basically a difference in the lock and key complex with lactosidase. The same situation with inhibition of antibiotic-resistant bacteria as with viruses. There are many empirical studies, and here you see some sample of them, but the mechanisms are not clear. There are some reactive oxygen species, there are some enzyme inhibitions and metabolic inhibition and a number of others. And if we would look at more than 3,000 papers, we again see the same particles, same size ranges for the antibiotic-resistant bacteria. So the onset of these projects were to deliver the particles which can inhibit the viruses and inhibit under other circumstances the antibiotic-resistant bacteria. And it's actually equally bad or almost equally bad as the viruses. So 10 million deaths is going to be only due to the antibiotic resistant bacteria. There are many more than others. And then you might also be interested to know that many cancers actually don't kill you, but infections which are associated with the cancer does. All right, so how do we do it and what the goals here? If we look at the proteins and the nanoparticles, our goal to actually create a conceptual computational infrastructure to accelerate the search and engineering of these particles in order to form the targeted complexes for viruses or for antibiotic-resistant bacteria. And also it would be interesting from the fundamental standpoint to understand better how we can, for instance, engineer the particles in order to target specific proteins. Let's start by asking the question, what prevents us from doing it now by using the tools which have been developed for the protein-protein complexes? And there are many. So if you look at the literature, there is actually a very stiff competition between different groups which are designing code, including the machine learning code, how to do better and faster job by, say, predicting the folding of the protein and their subsequent formation of the complex. It doesn't work for nanoparticles because the descriptors of the proteins are actually specific to the, they're based on amino acids. Also, they're extremely computational intensive. So for folks here who are involved in the geometrical assessment of complex structures, it's basically testing how one complex geometry structure fits and similar or not, and there is scoring to thousands of similar proteins which are known to form the complex. So it is actually very difficult to carry out these computations, and they require quite a lot of power. For us, the power is maybe less of a problem, but the fact that we cannot really use the same language to describe the structure of the existing protein-protein algorithm to do this for nanoparticles. And we started with that. So let's try to base our step toward protein nanoparticle complexes with a different set of descriptors for the protein-protein complexes. And let's see after that if it works or not. But we should be able to extend the same set of features from, say, this type of complexes to the complex when, say, the purple part, the protein B, is the nanoparticle. In each case, that would lead us to some prediction of the free energy of delta G, and from that we can engineer the nanoparticles. The basis of our approach is on distance matrix. So it means that between, say, the amino acids or specific groups here, we establish the distance between, say, each of the group in one protein and other amino acids and the groups in the other protein. So this is, say, the distance matrix for the same protein, so it's inside, but these are the matrices which are AB. These are the most important. The interface between them is the parts where the distances are the smallest, and of course, when you are here and here, the distances are large. So we're particularly interested in the classes of, or the segments of these matrices, which are the closest to each other. So we developed a number of the descriptors in order to account for the similarities and the differences between the proteins and particles. First, just like for a number of protein-protein complexes, we used the chemical descriptors, or they are abbreviated as CH, and they are based on charge of amino acids or hydrophobicity and the number of carbon atoms there. The other two types are geometrical and the graph theoretical descriptors. Both of them are actually very easily extendable to the nanoparticles because they are based not on the chemistry of local collection of atoms, but on the parameters which are easily computable for inorganic and, say, organic molecules. These are its features. So inaccessibility radius, shell accessibility, pocketness, so how one and the other fit each other, and Ossipov Chirality Index. In fact, the Chirality Index has not been used in many approaches of the drug design. And the graph theoretical indices include the Ricci curvatures, the multi-fractal dimension, and Gaussian networks. If we look, for instance, at the chemical features, we can see how different these features are for one of the proteins that we used as model. You can see that, for instance, this side is related to the place where the other protein can lock in and form a firm, highly interacting complex. It can be aided by other parameters, but that geometrical features is very helpful. We can also see that the graph theoretical indices also very different for the same protein. So here the examples are the Ricci curvatures, they are all very Ricci, and Foreman Ricci. They're somewhat correlated, but also they have some differences, and we decided to include them both. The sense, the novelty and the usefulness of utilization of the Ricci curvatures is related to their description of the transport through the network. So if one would take the traditional network theory or graph theory, then one can apply the formalism of Riemannian geometry and look at the geodesics. In this case, these are the graphs which connect amino acids in the proteins. And the sense of the transport through this network is correlating with reconfigurability. So which part of the protein is the bottleneck, so to speak, for reconfiguration. Which part is more sensitive and most essential? And they can be correlated with some other features, but that importance of this dynamic behavior is quite critical. So the multi-fractal analysis reflects a different aspect of the chemical structure. So it creates the measure of local complexity. So how sophisticated this log and how sophisticated is the key. And the idea behind it that if the log is sophisticated, then the key needs to be equally sophisticated in order to fit it. The last segment here is the Gaussian network, and it is related again to the mobility of the structure, and that reflects very nicely, and it's important to understand what's possible there, how the structure can accommodate the other structure. So last but not the least, the chirality index is quite significant for all the biological structure. And as you can see, it's very different for different places. So unlike calculation of the chirality for the entire structure, which actually had not been done that often, although it could be very useful too, it's a nanoscale chirality. As you can see, the local chirality where the units are interacting is not, I mean, it's very different than what you expect. So it can be left and right, and that would correspond to what's left and right needs to be in the key and the log. And I like Wasipov index because it changes the sign if it's left and right, and you can see how significant it can be. The chemical features are actually quite standard and they are useful. And for example, you can see how the different sites also can be complementary or not. So now the concept here will be, so we have these descriptors, we have the matrix, the distance matrix. So each segment, each spot in this matrix have a number of parameters which are chemical, graph theoretic, and geometrical. So from the analysis of the multidimensional matrix based on the protein-protein complexes, we can establish by using the machine learning the protocols how to predict whether the proteins would form a complex, yes or no, or maybe even Ka, the prediction of the free energy, and where. And both of these features are important and not yet available in many other even established protein-protein algorithms. So here are some of the data. We used a number of methods, and in machine learning, we decided to apply several protocols. And as you can see, it may be there are some differences. For instance, in Gaussian bias or random forest or XGBoost. But there is also some parallels. They come across, in particularly when we compare the performance of the feature by feature. And as you can see, just by using the graph theory, we actually have a pretty good prediction. Just by using the geometry, we also have a pretty good prediction. But if we use the chemistry, it is not. And so, and it's actually across the board, across all the different methods that we applied. And that means that if there is a problem in establishing the chemical description, which would combine or which would be unifying for the proteins and nanoparticles, and there might be, then we can simply use these two as a combination of the geometry and the graph theoretical features as the predictor of the complexes and the sites. And as you can see, the difference if we use all of the features or use just the geometrical and the graph theoretical is quite small. In fact, if we look at the graph theoretical, it's actually outperforms, I mean, a little bit, the geometry. Other calculations that you will see later on, they will be based on only these two features. It can also be compared in this format, and you can also see the ROC curves. So these are for chemical features, and these are for all, and the combination of G and G gives you very good performance, especially for the neural networks. Let's have a look how it works for the prediction of the proteins. We use three different cases. In all three cases, it's a very good match. We were actually quite surprised. And this match comes across again across the number of the different algorithms, of machine learning algorithms. And as you can see, the ground truth and the predicted sites respond very well in alpha solenoid, in team barrel, as well as in SARS protein. So this is what we have as a ground truth. This is what we have in the algorithm that we have developed. Now, I'd like to point out that these two features again gives fairly decent, not decent, actually very good description of what we have for all the features and for the ground truth. So now we will apply geometrical and graph theoretical descriptors to the nanoparticles. And for instance, this is how we would describe the particle in the same framework as a distance matrix. And after that, we decided just to have a look initially. If we have the different kind of predictions for interactions of the nanoparticles with a specific protein, for instance, trypsin, if we change the shape. The nanoparticles here are graphene quantum dots or graphene nanoparticles, so they are basically made from a single sheet of graphene, and we can easily make this type of particles and this type of particles. First, let me make the point that indeed, if you change the shape, the size of interactions change, which is very good. If we can also look at one feature, so that is the chirality of the particles, it also affects the other side, as it should be in all biology. Now we decided to compare the performance of the algorithm that we have only based on these two descriptors with the molecular dynamics. It's done by other people. And molecular dynamics is a powerful method. I mean, it requires, as Hendrik would tell you, and I'm a big fan of it. And for nanoparticles, it does require a lot of good potentials, and not all the people are using these potentials. And unfortunately, this needs to be proliferated, but also the truth that it takes quite a bit of time. In this case, in this description, it is much faster. And we decided to compare how does it match or not the data obtained by molecular dynamics, for instance, in this paper for human isolate amyloid peptides. So these are assemblies which are responsible for diabetes in adults. And we can see that the match is quite nice. So the predictions that have been done by molecular dynamics and predictions which are done by machine learning are actually quite on the spot. The other test that we decided to carry out is also fairly new data. These are related to variability of the protein coronas. So there are many people who investigate the protein coronas, so how different proteins in plasma or in tissues absorb and form the shell around gold particles, silver particles, and carbon nanotube particles, and carbon particles. And people are basically puzzled why some proteins are absorbed and why some are not. And these questions are actually posed in this very nice paper from Markiti Landry group in Berkeley. And you can see here that they found by mass spectroscopy that albumin actually is depleted. It's a very typical transport protein, so it absorbs to the particle, but for the carbon nanotubes and spherical carbon particles, it's actually pushed out from the corona. But in the same time, the apolipoprotein, histidine-rich glycoproteins are enriched. And the enrichment here is very high. And we ran the same predictions on our algorithm. I saw to our happiness that albumin is also pushed out from the corona, so it doesn't absorb as well as galactine or histidine-rich glycoprotein or apolipoprotein. What does it mean? That means that the explanation why some proteins are in corona, some are not, which so far had been the mystery, can be actually answered by this algorithm. including the prediction of size. And of course, after that, they can be looked by molecular dynamics and by experimental tools. One thing that I asked Jong to carry out as a test. These are the absorption sites for the nanoparticles of different chiralities. So if the algorithm is accurate, that means the adsorption sites for a protein, for the same protein, for the nanotubes of different chiralities. First, they should be different. Second, they should have a mirror image. And this is indeed the case. So with that, I think we have quite high confidence that the performance of this algorithm is just on these two techniques is actually quite high. And of course, there are a number of potential improvements which are possible here. And one of those, which I think is, I don't want to make a wrong impression that I don't like chemistry. I actually very much in favor of it. I think there is a very good case for further improvement of this algorithm for the nanoparticles and the proteins if we find a proper language, proper parameters for the chemical description of the interacting sites. Then we can increase the accuracy from, say, 85, 87 to maybe 99. And I think that this, the pathway to that has to come through the question, what are the properties that matter and how we can quantify these properties for the nanoparticle surfaces and sites which interact and the proteins. And I think that's, again, has to come from some molecular dynamics answers. With that, let me talk to you about some other works that are related to the graph theory. In this case, these are less about the machine learning at the moment and more like the first stage, so finding the right descriptors. And this is again involving biological structures. And the original question was for the description of the structure of cartilage and many other fibrous tissues. They're made in a very complex network. And if somebody would ask a chemist or a biologist what the structure of the cartilage is, they would show you that photograph and say, this is the structure. Well, we need to have some quantitative answers in order to engage the machine learning. And that's what we set up to do. With that, once we gain the quantitative traction for the network at the nanometer scale, we have to think about the quantification of the structure at the interfaces. In fact, this is not just a question of the cartilage, but many other materials which are being developed by multiple groups. And the components are pure nanoscale. They may have some biological components as a matrix, as a polymer there, but may not. So one of them are the networks from carbon fibers or graphene, or copper wires, or even the boron nitride nanotubes. In each of these cases, you see, again, if I ask you the question, what's the structure of these materials? We will not be able to give you the structure just like in the crystals. Say it's a cubic lattice or hexagonal lattice. We need to use something else. And these materials are actually very high performing structures, and this can be seen across the biological components or the nanoscale components. It can be light, strong, conductive, transparent, and the engineering of these properties has to come through the structure and therefore has to come through the quantification. So the goals of this project was to understand the approach, how we can describe these nanocomposites. We can call them percolating networks. It could be some other names. And then how do we understand the structure property relationships in them? Again, we can do it step by step. First, we will establish the quantification, then start looking at the correlation of properties. So just like in the protein complexes, I mean, if they form or not, if the properties correlation are there or not, and then apply the machine learning. In this case, we're not yet at machine learning, but the first two steps are being done. So with based answers to, or these dynamics of the project, the strategy on the graph theory description of the nanometer scale assemblies. It's actually quite simple. There is no kind of big network science finding here. It's just a useful application of simple graph theory. In this paper, I showed that we can use, say, nodes to describe the nanoparticles and their assemblies. And depending on what kind of inorganic components that we have to use a different type of elements to describe them. And one of the interesting findings there was that we can describe very complex structures and calculate the so-called complexity index. After that, we started thinking, all right, so now we have the tool to apply to a number of nanoscale composites, including the percolating network composites. Just like with the rods, we can look at what kind of element we should apply to the nanofibers, and quite logically, it's to graphs. And these edges are filaments, the nodes are intersections, and after that, that's very, very straightforward. The part which is not that straightforward is actually how to extract that information from experimental data. And the aim would be to use the graph theoretical indices or other features, for instance, the multi-fractal parameters, just like in the proteins, in order to describe, say, cartilage and other composites in this term. So it's not crystal lattice, it's not a cubic, hexagonal, or some other, but rather say it is a network which has, say, average nodal connectivity X or average closeness centrality Y. And by say, and one would expect, at least I would expect, that depending on the connectivity, we would have the different type of properties, for instance, mechanical properties. So we started as the example with the network of aramid fibers. These are the examples of those. And the case for them can be very hard to do by using the traditional means. They're very nice material, but how does, say, this bulk structure is different from some other bulk structures made from the same aramid network is not very clear. And we decided to extract that organization for the networks which are made from different concentrations of aramid monofibers, and they are real membranes. So it's not just a simple a case for a fundamental study. There are quite clear applications for them. And indeed, we made a number of these networks. We developed a special program which takes SEM images and process them, finding nodes and edges, so intersections and fibers. And Drew was the key person who spent a couple of years on perfecting this approach. And eventually it is available now on GitHub. We can do it reliably on pretty much all the quality SEMs and transmission electron microscopy images and confocal images. We process them and ask the question, do we have the correlation with the properties? And do we have a trend in some graph theoretical indices? The answer was yes. So we do have a trend depending on the concentration. And for instance, the average clustering coefficient is very much in line with the increase of Young's modulus. Note that toughness is non-elastic property. A prediction of toughness is hard. And every person who would work in mechanics would tell you that this is some of the difficult questions. And for instance, Horacio had spent quite a lot of time on that and developed the machine learning tools. It turns out that indeed here we also have the correlation with toughness. And of course, these are just initial steps, and eventually we would like to understand better the essence of this correlation, the physics, and how we can apply it to a number of different approaches, the networks. But the point is that this is the example how we can apply, for instance, simple findings for the network of the same position. And of course, the average clustering coefficient, when you have the triangles or the density of the triangles, is logically connected to the mechanics. So the triangular segments are very convenient for efficient stress transfer and mitigation of the local defects. And for that reason, I think it's actually fairly physically straightforward why this parameter is correlated with these mechanical properties. The Wiener density is actually correlated with van der Waals interactions, and these fibers are connected through the chemical and van der Waals interactions. And of course, after that, we looked at some applicability, and it turns out that these composites can be actually used in some robotics and devices as a part of the batteries. If you're interested in that, I can elaborate on this more. Importantly, that now the question is, do the indices change depending on the type of the network? Yes, they do. And we are looking now in the carbon nanotubes composites or silver and silver nanowire composites, for instance, those made by Kriti, and they are not the same. And you can see how different they can be. And this is a good thing because now we have the evidence that one network is different than the other, and we have the quantitative description for that. And that quantification will give us the passage to the machine learning. One very good example of that is the paper which had recently in 2021 was published in MRS Bulletin, and it analyzes the aramid nanofiber network as opposed to or in respect to the collagen in cartilage or the gold wires. So we say that aramid nanofiber is similar or not to the structure of the network in cartilage. But how do we know? Is there a strict, rigorous proof of that? I mean, we can visually say that, yeah, it's kind of the same. And are this the same here or not? And we decided to apply the StructuralGT processing of this SAM images. And after that, we evaluated sets of theoretical descriptors, and you can see over here. And the fun part is that, and I was stunned by this, I mean, it was a good day, that the descriptors that we found for cartilage and NF almost overlap. And there are some differences in gravity density. In fact, for NF, it is a little lower. That means that actually lighter. There are big differences between them and the gold wires, and that can be related to what they're made of. So that means that by looking at the structure of the network, we can infer what it is made of, and vice versa. So we can make first the component and then the network with a particular structure. So again, here it is a very good case for complex dependencies, the non-linear dependencies, how the, say, the graph theoretical description and geometrical description of the element, say the golden wire or fiber, are related to these network which we have in the end. And this is again not for just fundamental reasons. Of course, this was the part which the fundamental part excites me quite a bit, but we need to justify it, and the translation of these findings was done for engineering of insulating layers, which are based on cartilage-like structure, and these insulating layers for implants are outperform every other insulating film that we know. And this is because the mechanics is good. And also the stress transfer as we bend is very efficient. Also important that this this network allow the strong adhesion to the surface. So all these fibers, they actually interact not only with themselves, but also with the implant surface too. With that, I would like to thank you all for this conversation, and would be excited to answer any question and discuss any potential problems that you can see. So have a fantastic day.
Thank you so
Nick,
much.
as I wrote in the, I unfortunately I have to teach now, but I enjoyed your presentation very much. Fantastic work and very, very interesting ideas. So I'm looking forward to learning more about them.
Thank you, Haras. You have a great class, and yeah, thank you.
Bye,
See
guys.
you later.
Bye.
Mm-hmm.
Bye. Yeah, it's amazing. Actually, also for the latter part, I was very curious. You know, these different categorizations. You know, I mean, for different nanomaterials, you know, that look really, yeah, they give a different fingerprint of what matters in terms of descriptor. It's really more, yeah, a lot of food for thought.
That's what I hoped for, and God, I mean, help us in our strides to get the center, and that's what I hope to, to do as a part of the center, to expand on these ideas and to figure out how this language of these irregular networks, or how the language of proteins can be translated in the language of the nanoparticles and find an Esperanto type of descriptors which would unite them both. And I think this is possible. We just started it, and there are many tools which network science had developed here, very complex tools, and I'm confident that the complexity of interactions can be matched by the complexity of the mathematical description.
Yeah, thank you for a very nice talk, Nick, and definitely the shape descriptors part resonates very well with my interests, and I'll bring it up again in my talk in a couple of weeks. I think one, since most of my work has been on macro shapes and not materials, one interesting difference is the homogeneity that is, if I give you a point in the material, does it matter to know where you are? Do locations have?
Yeah, that's a good point. I think what next step should be is to answer exactly that. So if we have an SEM image or even 3D image, does it represent the entire material or not? We have to deal with a finite piece of the network.
Right.
And how does the border affect what we know or what we learn? And that's, I think that's one of the very fundamental questions. Very good point.
Thank you.
Thank you. And I'm looking forward to your talk in 2 weeks.